Hello friends, in this video I will explain how to solve the problems on one-dimensional bar elements. The problem statement goes like this. The figure shows one-dimensional bar subjected to an axial loading. Considering it as two-bar element, determine first one nodal displacements, second stresses, third reactions. Looking at the diagram, the left end of the bar element is completely fixed. At the right end, a load of 10 kN is acting. Length of the bar element is given as 1000 millimeters. At the left end, extreme left end, you can see that there is a small arrow mark with X that indicates left side direction is a assumed positive direction. The force which is acting opposite to this, that has to be taken as negative. That is, load P acting opposite to this direction, that is X direction, that has to be taken as negative 10 kilonewton. The cross sectional area A is given 10 to the power of 4 millimeter square. Young's modulus E, that is given 200 gigapascal. Now we will solve this problem step by step. In the first step, that is FEA model, there we have to draw a line diagram of bar element, and we have to give the node numbering. Node numbering is one of the important step. Node numbering, in this problem I have started giving the node numbering from right side to the left side. At the extreme right side I have taken that as node 1 and middle one as node 2, extreme left side as node 3. Since in the problem they have clearly mentioned that taking into two elements. Taking into two elements means we have to divide this bar element into two equal parts. That's why we have divided into two equal parts. One is E1, E2. Length of each element that remains same, 500 millimeters, 500 millimeters. That is L1 equal to 500 millimeters, L2 500 millimeters. Here node numbering you can give from starting at the left side, ending at the right side also. That is also possible. And Q1, Q2, Q3 are displacements at node 1, 2, 3 respectively. F1, F2, F3 are the forces at node 1, 2, 3 respectively. At node 1, a load of 10 kilonewton is acting, that is F1 equal to 10 kilonewton. We will take it as negative because it is opposite to the assumed positive direction. Second step, finding the elemental stiffness matrix. General equation for that is K equal to AE upon L 1 minus 1 minus 1 1, where K is the stiffness matrix, A is cross sectional area, E Young's modulus, L is length of the element. Here it is L1 because it is stiffness matrix of element 1. You have all the values. A 10 to the power of 4, substitute that. E 2 into 10 to the power of 5, L1 that is equal to 500. E equal, I have taken as 2 into 10 to the power of 5 because in the question he has given as 200 gigapascal. All the dimensions are in millimeter, so I will convert that one into millimeter square, Newton per millimeter square. So it becomes 2 into 10 to the power of 5. Now this part AE upon L1 that you calculate, we will get that value as 4 into 10 to the power of 6. For simplification purpose, I will take that 10 to the power of 6 outside. I will keep it as it is. Only that value 4 I will multiply inside the matrix. Now stiffness matrix of first element becomes K1 equal to 10 to the power of 6, 4 minus 4 minus 4, 4. And we can see there the column numbers and row numbers are given. Column numbers are 1, 2. Row numbers are 1, 2. Why these numbers 1 and 2 only? Why not 2, 3? Why not 3, 4? This we will clarify looking at the FEA model diagram. See here, for element number 1, the nodes are 1 and 2. Hence, for K1, the row and column numbers are 1, 2. Next, we have to find stiffness matrix for element number 2, K2. Equation remains same, AE upon L2. L2 is length of the element 2. Substitute all the values. Here, for this problem, area remains same, Young's modulus is remaining same, and length of the element 2 also same as length of the element 1. Hence, that part, if you calculate, that also value remains same. You will get as 4 into 10 to the power of 6. Here also, I have taken 10 to the power of 6 common, that is, I have kept it outside. Only 4 I am multiplying inside. Common, whatever you are taking outside, that should be same for all the stiffness matrix. Then only you can add easily in the further steps. 10 to the power of 6 is common for same outside in the K1. Same value 10 to the power of 6 is outside the matrix in K2 also. Here the row and column numbers are 2 and 3 because for element number 2 the nodes are 2 and 3. That is the reason row and column numbers are 2 and 3. Next step is finding the global stiffness matrix. Global means for entire. For entire element we have to find stiffness matrix. That we can find by adding K1 and K2. The equation like this, K equal to K1 plus K2, where K is global stiffness matrix. K1 is the elemental stiffness matrix for element 1. K2 is the stiffness matrix for element 2. Now, finding the global stiffness matrix is one of the important steps. So, to find that, what I will do, first I will write a matrix keeping blank. Inside I will not write anything, only the common term 10 to the power of 6 I will write, and square bracket I will write it. 10 to the power of 6 I have not written here, that is missing here, you have to write it. And write the column and row numbers. I have written 1, 2, 3 as column numbers, 1, 2, 3 as row numbers. Why 1, 2, 3? Because there are 3 nodes, hence size of the global stiffness matrix becomes 3 cross 3. That's why I have written. Now, in the place of column 1, row 1, what I have to write, that we will see here. Now, after finding, we will get this as a global stiffness matrix. Okay. See here, in the place of column 1, row 1, I have written as 4. This 4, how it comes, that we will come to know looking at K1. See here, at K1, at column 1, row 1, it is 4. Hence, I have written there 4. Next, in place of column 2, row 1, I have written as minus 4. Come back. At column 2 and row 1, there is minus 4. That's why there I have written as minus 4. Similarly, you have to go on writing all the values. But in the place of column 2 and row 2, I have written 8. This is because, come back, look at K1. At column 2 and row 2, there is 4. Similarly, in K2 also, at column 2, row 2, there is 4. Since there are 2 values in that place, so we have to add those 2. 4 is there in K1, and in the K2 we will find it as again 4. So 4 plus 4, that becomes 8. See, I have written that 8 in the place of column 2 and row 2. And in the place of column 1 and row 3, I have written 0, because in the both stiffness matrix K1 and K2, we won't find the place or that value column 1, row 3. That's why I will take that value as 0. Similarly, in column 3 and row 1, there also I have written 0. In this way, we have to find global stiffness matrix. Next step, step number 4, nodal displacement vector, that is q equal to q1, q2, q3. These all three values we have to find now. Next step number 5, global load vector. Load means force. F equal to F1, F2, F3. F1 is minus 10 into 10 to the power of 3, that is load acting at node 1, that is clearly given in the diagram. Negative sign because it is acting opposite to the assumed positive direction. F2 is 0 because at node 2 there is no force is acting. F3 is also 0 because at node 3 there is no force acting. Next is step number 6, that is equilibrium equation. The equilibrium equation goes like this. K into Q equal to F. K is the global stiffness matrix. We know that. Write down. Q, global load vector. That also we know that. That is in the step number 4. That also we can write down. Equal to F. F is global load vector. In the step number 5, we know that value. That also you can write down. After writing, this is the global equilibrium equation. Next step, step number 7, imposing boundary conditions or applying boundary conditions. This depends upon which method we are using to solve the problem. Here I am using elimination approach to solve this problem. So we have to eliminate particular row and column. Why to eliminate? Which particular row and column has to be eliminated? That we will come to know by looking at the diagram. There is one concept, wherever the displacement is known for us, that particular row and column has to be eliminated. Let's come to the diagram and see there. At node 3, it is completely fixed. Hence, the displacement at node 3 will be 0. Now we came to know that displacement at node 3 is 0. Because displacement is known at node 3, hence we eliminate that particular row and column, that is row 3 and column 3 has to be eliminated. You can see that there is a line mark, that is elimination mark that I have put. Now this is elimination method. Now in the next step we write down only remaining values after eliminating. Here I have written the remaining values. 10 to the power of 6 into 4 minus 4 minus 4, 8, Q1, Q2, then equal to minus 10 into 10 to the power of 3 and 0. And this matrices I have written in the form of equation for simplification purpose. For simplification, you can use any methods whichever easy for us, and solve that. We will find Q2 value and Q1 value. Q2 value we are getting as minus 0.0025 millimeters. Q1 equal to minus 0.005 millimeters. The first part of the problem is over now, that is finding the displacements. Next step, that is step number 8, finding the stresses. This is the second part of the problem. The equation for finding the stresses goes like this. Sigma equal to E upon L minus 1 into 1 Q1 Q2. For element number 1 we have taken as Q1 Q2 because for element number 1 nodes are 1 and 2. That's why we have taken as Q1 Q2. Now we know that E1, L1, Q1, Q2. Substitute all the values, simplify, we will get the answer as 1 megapascal. Similarly, for element number 2, sigma 2 equal to E2 upon L2 minus 1, 1, Q2, Q3. Q2, Q3 because the nodes for element number 2 are 2 and 3. That's why it is taken as Q2, Q3. We know these all values, substitute that and simplify. For this also we are getting the answer as 1 megapascal. Now second part of the problem is over. Now last part, that is finding the reactions at the support. Equation for that goes like this. R equal to K Q minus F. R means reactions, K is global stiffness matrix, Q load vector minus F. F means Q means displacement vector, F means load vector. Substitute all the values. This is equation after substituting. Now for simplification, what I will do? First I will multiply K and Q. Whatever the matrix we will get, that I have written there, minus of F. Now subtract these two, we will get the answer like this. R1 equal to 0, R2 equal to 0, R3 equal to 10 into 10 to the power of 3 Newton. Now third part of the problem is also over. Now we found displacements, stresses and reactions. All the answers I have written here at the end. This is the method to solve the problem on one-dimensional bar elements. Thank you.